right? Need 1 minute. I always make the slides in 2 versions, the handout version that I upload without all the animations, and then the ones that I have on here. And if I pick the wrong one, then it doesn't match with the page numbers, and all the handwritten notes appear on the wrong page, right? What's that? No, but I essentially prepared the website and then forgot to upload it. So I could just do it now if that helps anyone. Since you're sitting there with laptops anyways. Okay, slides should come up on the website hopefully now. You might have to refresh because it's cached on GitHub pages. They're a bit preliminary. I modified a lot in this next part because a lot of people didn't seem super familiar with linear programming. At least when I asked did I ask in the lecture or in the tutorials? I don't recall. But there was a lot more people, and it seemed most hadn't seen it much. So I thought it's worth adding a few more comments on that. Okay, that looks better now. So one last thing. Come on, you can do it. There we go. All right. Good. Then let's start. I have a little live demo for the next part I wanted to prepare before we start. Good. We were mostly done with what I wanted to say about the parameterized complexity theory and parameterized reductions, and how you can prove that a problem probably doesn't have an FPT algorithm. But I think the end was a bit rushed last time, so I wanted to briefly recap the main message there. So a very brief recap of the parameterized hardness part that we've seen. We went through a bit of a detour to find the right definition, and basically I wanted to give you some reasons for why the definition may be not the most natural one that you could come up with for this class W1. But really the end of the story is that W1 is the class that you want to show reductions against. there's a very easy way to show that a problem is in W1 using either the k-step halting problem or just from the definition that we used with this tail non-deterministic, kappa restricted, non-deterministic random access machine, which is a long term, but all it says is you do the usual kind of RAM program and you're allowed a little bit of non-determinism, but only in the last f of k steps. And if you can solve your problem with such a machine, non-determinism only at the end and only for some amount of time that is bounded by the parameter, then the problem is in W1. Equivalently, you can reduce it to this halting problem for a Turing machine. I think the other is a bit more natural. And then we've seen there are further complete problems for this, and independent set is one of them as well, which followed from this the specific weighted satisfiability problem. Now the slightly annoying part here is that we couldn't do the full proof because it I looked into this again, and it just gets into a lecture on logic, and I felt this is not where we want to go. There's more direct ways to prove this, which you can find in Segan et al. In this book that is referenced on the website. As one example, what else you could have as problems that might or might not have a fixed parameter tractable algorithm was this partial vertex cover problem, where it's like vertex cover, but now you're also telling, as part of the input, you're telling me how many edges I have to cover. I get to choose which, but you get to tell me how many. And it turns out this makes the problem really hard. It's a W1 hard problem, so with this parameter, it doesn't seem that there's an FPT algorithm. And there was a reduction from independent set that we went through over quickly. Basically, by adding these blue vertices, we make the graph regular in terms of the original vertices. And so if you had a vertex cover in the original graph, you cover exactly these disjoint edges, and that's an easy number to count. And if you give me that count, that's the only way to cover that is by picking not vertex cover, independent set, by picking an independent set in the original graph. Now, to kind of wrap up the story a bit, what I never had on the slides, but I think is important to state, and I think verbally I said it, we don't believe that W1 is a subset of FPT or is the same. In fact, the widely spread belief is that it is a superset, but a strict superset. So problems can be in W1, but not in FPT, which means they may not have an FPT algorithm, right? Although they're still solvable with this specific non-determinism at the end. And indeed, you can tie this to a different hypothesis from complexity theory that will come haunt us in the next section, the exponential time hypothesis. That's what ETH stands for, which is fairly widely believed. It's stronger than NP not equals NP, but it's I guess there's more evidence for it than for some others. And so this also implies if this exponential time hypothesis is true, it means that these two are separate. FPT is not the same as W1. So really reducing problems to a W1 hard problem makes it very unlikely that it has an FPT algorithm. I wanted to say that a few times more to be super clear. Okay. We've seen reductions need to take the parameter into account, but that's actually the part where the natural definition just works. You have to make sure the parameter stays bounded in terms of the original parameter, and that's pretty much all that you have to take care of. It might mean that for some reductions between problems, you need to come up with new ideas. What we didn't dig into is further details of the complexity theory. You can further structure. You may have wondered why this is a W1, and you can have other parameters there. but the classes only really become different types of complexity classes. To define them properly with this general T, you need to define them via some specific property of the formulas that you do weighted satisfiability on. And it's a lovely piece of theory, but for the message of does a problem have an FPT algorithm or probably not, it doesn't add any extra punch. Essentially, it's usually the dichotomy. If you can find an FPT algorithm, you know what you're doing. And otherwise, you can probably show it's W1 hard because that's the easiest of the hardness classes. All of these WT classes are even bigger. So W1 hard is usually enough. As an example that we didn't look at is the dominating set problem. It's a bit like vertex cover, but now you're picking vertices to cover all the vertices in the graph. Either you pick them directly or you pick one of the neighbors. That's a dominating set. And you can show that it's W1 hard, but actually it's unlikely to be in W1. Indeed, it's W2 complete. Probably that's a strict inclusion again. But in terms of the message as an algorithm designer, it doesn't make a big difference. Just don't bet on finding an FPT algorithm for this problem. Exactly how hard it is, maybe not so important. Okay. Any general questions on this part? So lower bounds in terms of parameterized problems via reductions, particular to these W1 hard problems. You'll have some, on the upcoming exercise sheet, some more examples of this. So hopefully after that, at the latest, it's clear. And what I mentioned earlier, there's this book, Sigan et al., that's Parameterized Algorithms, I think is the title. They have a chapter on reductions as well, even though this is not their focus. They focus on the algorithmic techniques, but they have some chapter where they do a few reductions in full detail. So if you'd like to see some more examples, you could go there. And you see there's a few that we've seen: partial vertex cover and independent set and dominating set, what I just mentioned here, and different reductions between them. And I will leave it with that. Then, okay, if you want to break the ties on LPs. So LP stands for linear programs. We'll look at that again. So originally, when you check the original list of topics for the lecture, there was a unit planned much later, specifically on linear programming. And I think I'm moving a little bit away from delaying it for so long. And instead, we'll do the first half today, and then some secondary bit, the duality at a later stage where it's used. Even if you've seen LPs before, I hope you learned some new tricks there, because the typical lecture on linear programming would be some mathematical optimization lecture, and often the focus there is a tiny bit different. They very much stress the linear algebra part and not so much maybe the applications. Maybe data science is different. Is, I guess, a standard tool there too. Okay. Okay, it's definitely too early for a break, so let's dive into this. In the next unit, we'll look at some more advanced ideas for still parameterized algorithms. both upper bounds and lower bounds, things that deserve a bit more context. And so I took them out of the other two units. Conceptually, they belong in the previous two units, which were about algorithms with parameterized techniques or lower bounds. But these felt they're distinctively more involved and built on some extra steps. So I split them off to have the space to devote a bit more time to the setup. And hopefully the techniques go well beyond these specific examples. What we'll start with today is a bit of a detour first on linear programs and linear optimization. And then we'll apply LPs. The first application we'll see will be for a better kernel for the vertex cover problem. And there's a short section at the end also on some advanced lower bounding techniques. So far, we've really had this dichotomy. Either there is some FPT algorithm with an arbitrarily bad function, potentially, f of k. F could be a really fast-growing function. Or it's W1 hard and we don't expect any kind of FPT algorithm. But for problems where we do have an FPT algorithm, we might want to know if we can say something about this function f of k. A specific algorithm always gives you a specific function, and that may or may not be a good one. It'll be super polynomial, but maybe it's not clear how far you can push it down. And there we'll see some techniques with stronger assumptions, giving you some lower bounds that go beyond saying there's no FPT algorithm whatsoever. That's the plan. Let's start a bit with the practical side of linear programs first. And so I pitched this really for people who've never seen it. If you've seen it, maybe the first part is easygoing. What are linear programs? First of all, the name, I guess, is just showing the age of the technique. It's from just after World War II. And a program at that point didn't mean a computer program, really. There were no such things in widespread use. Instead, it's more the planning, or a program was a schedule, rather. So think of it that way. It was motivated from the application to call it like that. It's a bit like dynamic programming, same kind of era. So what are they? The name is just what it is. I guess it's here to stay. It's a class of optimization problems. And unlike most of the things that we deal with in this module and most of computer science, it is about continuous optimization, not discrete or combinatorial. It does have a combinatorial flavor to it, but we'll come back to that. So it's always something you want to minimize or maximize. That's what optimize means. And there's some side conditions that constrain you in doing that. Now, the interesting bit about linear programs is that they can be solved exactly in polynomial time in a completely clean sense. So I didn't define the formal problem to say in P we would have to say what the decision problem is. And then really the decision problem is a bit less exciting maybe, because it's really just talking about linear inequalities. But yeah, so the appeal of linear programs comes from the fact that we know solvers that can solve them worst case polynomial time. And they can also be solved in practice for really large instances. I mean, one reason is that it's a polynomial time algorithm, but also because of its widespread use, people have tweaked these algorithms and made them really clever. So it goes far beyond saying there's some polynomial time solution. It's a bit like SAT solvers, which are often fast in practice. But here the difference is also in theory, these solvers are clearly polynomial. Okay. The specific names are maybe not so important. If you've seen LPs before, you've probably seen the simplex algorithm and maybe know that that one's not polynomial in the worst case, but there's other methods that are. let's introduce what this is about with a little whimsical example. So suppose you're an apple farmer, and you're trying to maximize your profit, but of course there are constraints of real life that stop you from just earning infinite money. I guess the way to earn infinite money is to have as many trees as you can think of, and also sell your apples at infinite prices, which for various reasons won't work. So the real thing is modeled here like this. So you're devoted to promote the varieties that have grown in the area for long and have picked. So these are like the last 2 years of Hesse's specialized apple varieties that they picked as some historically relevant varieties. Doesn't matter so much. They're just 2 names, Sossenheimer Rote and Korpacher Edelrennet. Two types of apples, and that's all you're gonna do. You plant trees of type S or of type K, if you prefer. Now they have different yields, and also the apples yield different prices. So here we're just saying per year, 1 tree of each variety gives you a certain amount of money at the end from selling the apples. As he has an orchard of a certain size, and each tree needs a certain amount of space. And also they need fertilizer and time to harvest, okay? These are the main constraints. We have space constraint. We need to put fertilizer to get the trees growing, and they have different requirements there, just because this is a bit more sturdy one, and the other is a bit more needy. And then the harvest, I don't know how to justify the 3 times increase. It made the numbers work out nice. Suppose this is basically, what can we make up? So these you have to pick at the exactly right time, and for the others, it doesn't make such a big difference. You can pick them and they ripen after you've picked them. Now, the other assumption is that Hesse really has a tight budget and can only afford a certain amount of fertilizer per year, and can only hire people to do the harvesting for a certain amount of hours per year. And these are hard constraints at this point. So that's the setup. Okay. Yep. Question?
Everything in this problem must be linear in relationship to other things. Yes.
For linear programs, the question was if everything has to be linear. For linear programs, everything has to be linear. The way it's defined here, it actually is linear, because the amount of space per tree is a constant. The amount of fertilizer and time per tree is a constant, and the amount of money you get out is a constant. As often, this makes sense to a certain degree. I think it's fine that here things are proportional to the number of trees for a while. Now, clearly, nothing in real life is ever linear forever. Like if you were starting to plant 1 trillion trees, you'd certainly not receive the same price per apple than if you have a normal amount that doesn't just flood the entire world with apples. And similar, I guess for the other things, there's kind of limits where it starts to fall apart. But within reasonable constraints, I mean, we're constrained here anyway, so we won't grow 1 trillion trees. Locally, it often is a reasonably close approximation to reality to have this linearity assumption. And so it's the very critique that the inventor of linear program, George Danzig, got in when he presented to the math audience back in at that time his algorithm to solve those. And they also objected, yeah, the world is not linear, right? But it seems locally it often is sufficiently linear that it gives reasonable results. And LPs are used in logistics and planning and scheduling a lot, where this seems to be good enough. But it's, of course, a legitimate question. Here it's essentially, you can say, it's a modeling assumption. So the question is, how many trees of each variety should we plant to maximize the profit? And maybe also interesting if you think of it from a economic perspective, we're constrained by various things here. Which is the tight ones? Are we? Well, maybe you can try to make a guess. Like the result will be something. Maybe you can guess how much money can he make in a year from this orchard if he picks the best combination of trees. And what's the actual constraint that hurts us, that stops us from earning more? Do we run out of space or fertilizer or harvest hours or some combination? Time? You harvest hours? Okay. And any guesses for the overall profit? We can do some quick, like, so we're gonna have from the space, I guess, less than 1,000 trees and so on and so forth. You can do some quick bounds, right? It can't be more than 1,000 times this. So 250,000 seems like a very optimistic upper bound. It's probably going to be lower if you look at some of the other constraints. Now, this is a simple problem. Just there's two variables, right? The number of trees I grow of type S and the number of trees of type K. And the numbers are small, is all relatively easy to figure out manually. So in this case, you can work it out. In general, maybe you see already that this is helpful to have a computer help. So this problem is a classic operations research question. And you can write it down as an LP formally like this. We're trying to maximize the profit, which is 195, or maybe you have to go back once in a while for the numbers. 195 for each type S tree and 255 for each type K tree. So I'm just picking two variables, S and K, for the number of trees of type S and the number of trees of type K. And then we have some constraints. The easiest are maybe the last ones. We can't build negative trees. Why would that ever make sense? Yeah, you know, optimization problems sometimes do funny things. If you say you run out of harvest hours, the result could be that you do negative trees of one type to create time for harvesting from the other trees, which mathematically might work, but of course doesn't make any sense. So these are constraints that we need for that purpose. And the other three are just reading off from the slide. The total space is bounded by 4 times the total number of trees. And then for the fertilizer and harvest hours, you get these two. Okay? So far, so good, right? Okay, some terminology to bring this back to land of math and linear optimization. We call this thing the objective function. That's the thing we try to minimize or maximize. The direction of optimization is called the optimization goal. Well, we'll come back to all of these. And one of those inequalities is called the constraint. And we give the whole thing a name just to be able to talk about it more efficiently. Okay, what else? The variables, I forgot about those. I mentioned S and K, the number of trees. The implicit assumption is that these are always real numbers. Now, some combination, some values for the variables here in some is effectively a point in R2 is called a feasible solution if it satisfies all the constraints. You can pick arbitrary numbers, and that's always a value for the variables, but not all values for variables satisfy the constraints, of course. Then the largest possible value, or the best possible value in general for the objective function, is the optimal value. And we'll abbreviate that with set star, just have a short notation. And an optimal feasible solution, so a solution that's feasible and achieves the optimal objective value, is called an optimal solution. And we'll also denote this by the variables with a star. Now, this need not be unique in general, right? There could be many ways to pick the parameters, the variables, to maximize the objective, but any of these will be called an optimal solution. Okay, name's clear. So apart from manually messing with the problem, and in this case, that's good enough to figure out the optimal solution, we can also do a very systematic approach that will effectively lead to the simplex algorithm. Because it's in 2D with two variables, it's easy to draw. And so just to go over this quickly, we have a constraint for the space, which means I really should have put, so this is pointing this way, right? We're below this. Below this line are all the points that satisfy this constraint. So we've cut off this part of the region. No point up here can ever be useful. But all the points down here so far are fine. Now we can add one constraint after the other. For example, the harvest constraint is this blue line. So everything below the blue line is fine with that constraint. And if you take the two together, you get this region below the two lines, below the minimum of the two. So far, I guess I'm getting new lines each time. So that's the feasibility region so far. Now it's this region. Now we have a third constraint, right? The fertilizer. Aha, now you see actually the region is shrunk to this, and the space constraint is never really relevant. It's entirely outside of this area. So only points in this lower part can ever be feasible. What's missing is the non-negativity constraints. So the actual feasibility region is this purple shape here. In general, you can already see here, it's always going to look in 2D like a convex polygon. So a thing you get as the intersection of half spaces. So you take a line and everything to one side of the line. If you intersect an arbitrary number of those, you'll always get a convex polygon where all the corners, where all the vertices are on the convex hull of the thing. I don't know if that helps you. Okay, but that's not all. So we know all the purple points are feasible. They satisfy all constraints. How do we find the optimal one? And the graphical way to do that is to plot the objective function. And the objective function, you can say, I'm fixing all values for x and k, for s and k, that give me a fixed certain profit, say 50,000 euros. And they all lie on this line because the objective function, again, is also just a linear number. If you set that equal to 50,000, you get a certain line. And that's the one that's drawn here. Now, it looks like that's not the best you can do. You can plug in different values for the revenue, and you get a different line. And you see that with larger numbers, it just moves up and down. It stays in the same slope. Just the intercept at the y-axis is different. And you can keep pushing that line up until you start to leave the feasibility region. And so at this value, 155,500 euros is the point where you exactly cut this corner. And at that point, you have to stop. If you increase it one further, then you're outside of the purple. You don't cut the purple region anymore. Okay? Good. So that's the optimal point. And you could read off, you try to read off from the graph what the solution is, but of course you can just solve the equations. So what else can we learn from this? I mean, first of all, the solution tells us to plant 100 trees of type S, fine, and 533 and a third types, trees of the other type. That already hints at one problem. The solution could tell you things that might not make sense because it's continuous. But let's suppose this is not a problem in our case. We just give up one tree. And indeed, both the harvesting time and the fertilizer are tight at this point because we're lying on the green and blue line. So both of these constraints are maxed out. We could not have more trees for two reasons, if you want. Whereas the space is never a problem. In this case, it's boring because it lies completely outside. You could also have a line here where it would sometimes make a difference. But if you're Hesse, you know what to change now. You need to somehow get more fertilizer and more hours for harvest. Whereas you don't need to buy new land. Maybe that's a good thing. Okay. Questions up to this point? Yeah. It's given in depends what your task is. In this case, it's given, right? This function is the objective. I could have used the colors here. That was the objective function. Now, all that gives you is the slope of this orange line. And what it doesn't tell you up front is where to put it, in how high to put it. That's the task of solving the LP. But we'll see like this systematic ways to get there. I just wanted to make one point, namely that this is very easy to do in practice if you need to. So here's a little Google Colab with code to solve this specific problem. The setup is essentially taken from Google's OR tools, which makes this very, very easy to do. And that's all you need. So you define, well, you need to import some solver code and so on, but this is, as I said, I just took this from their documentation. The real problem starts here. You tell it the variables, S and K, and you can give them a range. So here, that's encoding the non-negativity constraints. It's between 0 and infinity, plus infinity for both variables. Then you put in the constraints, and by the magic of Python, you can actually give these as expressions, and it'll take them apart again. It's a pretty concise notation. These are literally the constraints we had on the slide, just typed up in Python. And you tell it what to maximize or minimize, and you say solve. And there's some boilerplate code to get the result, and then it spits out the answer. Okay. So if you ever need to solve an LP, don't try to invent your new algorithm. It's really not needed. And the thing is, as you know, 2025, if you know that there's libraries that do it that well, you can ask any AI assistant to write the code for you, so you don't even have to look up that part. I did it old school and copied it from the documentation, but the documentation also has another fun problem, Stiegler's diet, which is just the story is a bit fun behind it. The idea was this is person that came up with this problem before linear programming was invented. And so he originally solved it with some manual tweaks, but not optimally. And now it's kind of a standard thing. The setup was, how can you meet your nutritional needs with spending the least amount of money? And so he took what was known at the time, and this is 1940s. So people cared about calories and protein, not about fiber. And I guess calories kind of subsumes carbs, but it's not a specific, like it's not an extra item here. And a small selection of vitamins and minerals. And then he put in all the standard food items they could find and what they give you in terms of the nutritional value, plus a standard price in terms of, well, US dollars in the 1940s. So the numbers that will come out will look really ridiculously small, but take into account that there's a bit of inflation going on since then. I guess 40s to now is 80 years, so it should have doubled 4 times or so. Doubling every 20 years. Yeah, roundabout. Pardon?
Which column is the price?
Good question. So 1939 prices in cents is the third column. So this one, okay, 10 pounds of wheat flour costs 44 cents. Wow. And you can do the same. So you can set up the solver and automatically add the constraints without typing them up another time and let this thing solve. So if you do that, just because it makes one point I wanted to come to, it shows you what you should do. First of all, the annual food price is $40. Even if you take that times 4 or whatever inflation makes of it, that's not much, right? Now the catch is, what should you eat? A good amount of wheat flour, beef liver a bit, cabbage, spinach, and lots of dried navy beans. Yeah. So if you apply linear programming to the real world, it'll ruthlessly maximize the objective and stay within the constraints, but nothing else, right? And it also means you take all the slack out of a system, which sometimes, if you look at train timetables, etc., sometimes you get the feeling that there was one optimization function or one objective at the expense of some others. So that's always to be taken into account. The LP only tells you the solution in your formal model of what you put in. I guess the other point to say is, even if your problem is a tiny bit bigger, like in this case, has around 100 variables, it basically solves it instantly. You don't see anything. Okay, what's the general LP problem, apart from these concrete examples? In general, you'll have a bunch of variables, say n variables, x1 to xn. They're all real numbers. They may or may not be constrained to be non-positive, non-negative. I'll sometimes write this less and greater sign as just as a way to say there's nothing to see here. It's not a constraint of any sort. It just is an explicit way to write that there's no constraint for xj. And you can have actually 3 types of linear constraints. You can have some coefficients times each of the variables equal to some right-hand side that ties the values to some specific, or ties the values somehow down exactly. You can also have lesser equal or greater equal constraints. That's up for you, whatever makes it more natural to model the problem. And of course, here it's brought in the nice shape that all the variables are on one side and this constant is on the other side. Of course, you can, it's equations, linear inequalities, you can move things around. In general, if you write down such a problem, what can happen is one of 3 things. It can have a finite, clearly well-defined optimal value, like our examples. It could also happen that your constraints are actually contradictory and you don't get any feasible point at all. If you're not careful, this could happen. Then we call the problem infeasible, because there's not even a single point to pick, let alone an optimal one. And the other option is it could be unbounded. If somehow the constraints don't constrain you that much, you could make, like in this case for minimization, you could make the objective arbitrarily small, minus infinity. Then the problem is called unbounded. So that's one additional thing to take into account. For algorithms, they have to detect which of the 3 cases happens. And only in the first one, it makes sense to compute an optimal solution. As it turns out, all the algorithms for LPs can do that. And in polynomial worst case time, they can tell you which of the cases applies. And if it's case A, they can spit out the optimal solution, or a optimal solution. Okay. Let's see one more algorithmic example of what we can use LPs for. And this is maybe the oldest thing modeled as an LP. It's the max flow problem in graphs. So if you haven't seen this, the problem is given a graph with some vertices singled out S and T. And this in general is a directed graph, so it could be whatever, arbitrary. And think of these as directed pipes or streets with a certain capacity. So the capacities are just telling you how much flow you can send across an edge. I'm not going to write these down. The question is, how much flow can you get out of S and into T? Constrained by how much you can put on each of these edges in between, and the fact that you cannot lose objects in the middle or cannot use fluid in the middle. If there's 5 units coming in through here, 5 through here, and 10 through here, you should have 20 going out. Only in S and T there can be an imbalance. That's the max flow problem. The goal is to maximize what you can route from S to T, but that's actually the same as what leaves S, right? So we call that capital F. And then we have some capacity constraint on each edge. If you write that as an LP, it's a very naturally fitting in this shape. We maximize this flow value. The flow value is actually what flows out of S. So you can write that formally as, I guess I should say what the little f is. That's a variable for the edges. Each edge has an amount of flow that you can send across it. It's some real number. It's got to be non-negative because we don't allow negative flow in this case. And it should be bounded by the capacity of the edge. So f of the edge, I'm writing VW for the edge V going from V to W. So sometimes you would write it like this, or you would write it as an ordered pair. I'm using the more space economic version here. So the total flow you can write as everything that goes from S to some other vertex minus everything that comes back, because you could have edges leading back to S. And the other constraint, the not so trivial one maybe, is this flow conservation constraint. You have this for every vertex. That's what I said before. If it's not S or T, what goes in has to go out. And so this is what goes in, everything that comes from some vertex W and goes into V. And that has to be the same as what goes out of V into some W, summing over all the other vertices. And here these sums, it's a bit of a shorthand. You should interpret these sums. If there is no edge, then there's no summand for that vertex. So that's very, very well, it's essentially fitting exactly the form of LPs that we had. And so in undergrad algorithms, classes usually develop some tailor-made algorithms for the max flow problem. And indeed, you can, in general, solve this a bit faster than general LPs. But you could also take your network, encode it as a linear program, and let the LP solver do the rest of the work. Okay. Little break. This wasn't too technical today so far, maybe. Maybe not for everyone, at least. All right, shall we move on? So I hope you have some energy for the next steps. That was the introduction part. Now we'll look a little bit into some technical details because I felt it's worth knowing a little bit about the tools internally, how they work. In the next subsection, we'll look at some tricks to modify a given LP so that it still produces the same value or solves the essentially same problem, but has a different shape. And oftentimes that's the key to making progress on a problem. If all you're doing is modeling a problem and then passing it to a solver, that's not necessary. But we'll see oftentimes we use LPs as part of an algorithm and then want to do something with the output from the LP solver. And there it's helpful to be able to do some modifications to the problems. So we'll still think of this as mostly a tool. But another reason for looking at some of these reformulations is that they are also key to make LP solvers in the first place. And as I said, the goal is not for you to make your own but I think it's good to have a little bit of an insight how things work. You can always, any tool, as good as it may be, is only as effective as the cleverness with which you apply it. So we'll briefly look at least the conceptual ideas for the more basic algorithm for solving LPs. So first of all, recall this was the general form that we've just discussed. There's n variables, and then you can have constraints of different forms. So I'll always have n variables from now on and m constraints. And so the variables are called xj. The constraints have coefficients for the variables aij. So I is the constraint, it's the ith constraint, and then j is the coefficient in the ith constraint for the jth variable, as you can see in the examples above. And it'll have a right-hand side, which is just a number bi. And also the objective function, all of these have to be linear functions, so they have to look like this. Now, I guess for the objective function or general linear functions, you could have a constant term, but here for these, you could fold it into b, and for the objective function, a constant term doesn't make the problem different, so no reason to allow that here. Okay, as before, I hope this is explained wherever it's used. If set occurs, it's supposed to stand for the objective function, the objective value. The first step is to get rid of all these long sums and use concise linear algebra notation. So for now, that's just an abbreviation. If you've ever done programming in NumPy or MATLAB or any of these tools, they use this all the time, where everything is vectorized. And at least in the olden days, that was the way to get speedups in Python, by using the automatic faster routines that these libraries provided. Nowadays, you still do that, but you also rely on kernels that execute things on a GPU. But even if not, I mean, if you don't care about that part, ignore it. But you'll have to be able to read the matrix vector product notation for so many things in data science as well. I think it's worth getting used to. On the slides, I tried to be diligent to put a boldface variable whenever it's a matrix or a vector, just as a little signal. Remember, this is not actually just a number. I'll stop doing that after these sections, because in general, it's not actually that helpful, but and people don't consistently do it. But for the introductory parts, I was diligent with doing it. Right, so we have the variables, and instead of x1 to xn, I'll write the column vector x, bold x. For the cost function, we have the coefficients, that's another vector c. They have the same dimensions, but they're both column vectors. So if I want to get back the objective function, I should take the scalar product or dot product. And so I have to take the transpose of the c vector, because then c lies here, and x is a vector there. That's how you do dot products, put one, or, well, I guess from your perspective, put that on top of the other, as in matrix products, and you get back a number. So you can call this a scalar product if it's vectors, a vector space, or in general, a dot product is the more general algebraic term. That was the easy bit, that's the objective function. Then for the constraints, we can do both. We can fold the scalar product between the coefficient of one constraint and the vector of variables into a vector product. But we can also fold all the constraints in the other dimension into a matrix. So we'll write all the coefficients of all the constraints in one matrix. Here I'm just picking the equal constraints for now. We'll come back to the different types of constraints. So you have one big matrix with all the coefficients. You have one vector of the right-hand sides. And then you can write the constraints as the coefficient matrix times the vector of variables equals the right-hand sides. That's expressing the same as this line where we iterated for I from 1 to p. So you should imagine p copies of that. I noted down the dimensions of these matrices, so that's the assumption that there's p equality constraints, as up here. For the other two types of constraints, we do the same. Just note that when you write some vector less or equal some other vector, you have to tell me what the less or equal really means. But it's standard here to mean element-wise comparisons. So a vector is smaller than another vector if it's smaller in every component. It's smaller in the first component and the second and the third and so on. And same for greater equal. That's this standard notation for equal is actually the same. Like a vector is equal to another vector if the first component is equal and the second is equal and so on. Right? It's always an and between the element-wise comparisons. Okay, so that's how we can express the constraints. If we want to talk about a single constraint, you basically have to take a row of the matrix, of the coefficient matrix. And the notation I'm going to use for that is just put a bullet where there's the don't care dimension of the matrix. So I is the ith row, but then the columns, I'm saying take all of them. So you write this as this. So, you know, Python notation would probably be something like A and then I colon. And most languages have some way to say this. So colon instead of the bullet. But this is a bit, in the mathematical notation, this is more standard. And you can do the same for columns. Is that notation clear so far? Okay, so we can very compactly now write our LPs. There's a few other little, really shallow tricks we can do. The one is we don't need maximization and minimization. You can always write a max as min of the negative. You can just negate the cost function and minimize the negated. Or if you want to maximize revenue, you minimize loss. If you have greater equal constraints, you just multiply them with -1 and they turn into a lesser equal constraint. As also like I'm not going to say elementary school, but high school at best. There's a few more tricky tricks. To get rid of the lesser equal constraints, if you want to, you can introduce a new variable. So it's the same to ask for your variables to satisfy this constraint as these two together. So you introduce a new slack variable, which essentially quantifies how far is this away from the upper bound. And you request that that is not negative. That's the same. So you can move between equality and lesser equal constraints that way. And lastly, we can force all variables to be non-negative variables by splitting up the variable into two parts, essentially the positive and the negative part, and again, forcing both to be positive. It's not enforced that either of that always one of the two is 0. Turns out you don't need that. But you can replace xj with this difference wherever it occurs, and now get rid of xj, and then all the remaining variables are non-negative. Okay? So you can always eliminate these unconstrained variables. And with these rules, you can get your LPs to have one of those two normal forms. Which one is more convenient depends on the way you look at it. Either you have only lesser equal constraints with only non-negative variables, or you have equality constraints with only non-negative variables. In both cases, we'll write A as this matrix m times n, and B is as big as we have constraints, C is as big as the number of variables n for the cost function. But in these two regimes, so if you think about this case, with equalities, you probably want fewer constraints than variables. Whereas here you might have more constraints than variables. Potentially, it's not enforced. On this side, if you have more constraints than variables, then essentially you're constrained to a single point, or it's infeasible. So most of the time here, you'll have a lot of variables, maybe coming from slack variables. Whereas here, you could have a lot more constraints, and you take the intersection of all those half spaces. With that setup, I think I can tell you how the simplex algorithm works. Not in all full details in how it's implemented, but enough that you could, I think, work out the details if you wanted. And I realize some people have seen this before, maybe not in exactly that way. Everyone explains it a little different. I'm going to do a combination of two explanations. First is I'm trying to give you a geometric intuition, because really LPs are not that hard. It's a very simple concept if you look at it from this perspective. So here, I'm going to take this first normal form where we have less or equal constraints. And potentially many of them, many more than variables, and it still makes sense. Again, here to make things simple, n is 2, so the number of variables is 2. I can still point it, draw it in the plane. Each of these constraints, less or equal in 2D, is essentially one of those lines plus a direction, which is not drawn, but all of those kind of point in some way. And to make the picture look sensible, I guess you have to point them all in this way. So an individual constraint is basically telling you everything on this side is okay. If you take the intersection of all those half spaces, then you get some specific feasibility region. So here for notation, I'm going to write hi for the half space of one constraint. So all the values or all vectors that satisfy this constraint. Okay, but really it's the area below a line or above a line in this case when n is 2. And then the intersection of all these gives you this feasibility region, the yellow part. In this case, again, I'm assuming that these all point towards the yellow bit, which is not drawn in the picture. You can also see from the picture there's some constraints, like in our Hesse-James example, that don't even contribute to the feasibility region. They're redundant. Whereas the actual contour of the feasibility region is formed by potentially many constraints. Okay. Now, what about the cost function? In general, the cost function, I drew it before as this dashed line. And it's in 2D, it's some line with a certain slope, but I can always, visually at least, think of rotating my picture so that this dashed line is a horizontal line. Okay. Now, how to do the rotation with linear algebra math, I don't care for now. You can just change it to a different base. But suppose for now, or maybe make it an assumption that the orange line is horizontal, which means if we move the objective value up and down, we move the orange line up and down, which means the optimal value will be the lowest point in the feasibility region. And so you can physically imagine you put some marble in this yellow space and it'll just fall and roll down to the lowest point naturally. And here, clearly, it will end up here. Okay. And again, in 2D, this is very simple, but this actually works in general in just the same way. C itself, so brush up your linear algebra memory. A vector in full dimension defines a hyperplane, namely all the, for example, all the vectors that have scalar product 0 with it. And the same vector is also the normal vector standing on that plane. And that's really what this green arrow is. So this is the hyperplane for C, and that's C itself. It's pointing downwards. So really C you can think of as a direction for improvement. That's where you have to move. And this works in any number of dimensions. So this is already showing a bit what the algorithm does, but imagine you have a marble that somehow sticks to the boundary. Then it would still roll down step by step until it stops in the optimal point, just following gravity. Or imagine a magnet pointing downwards. Okay, if you take enough half spaces, I guess this is hyperplane, not half space. Half space is everything below a line. The hyperplane is the generalization of a line. And if you take n such lines, here 2, then you get a single point. Now, what's the connection between half space and hyperplane? The half space has some boundary, and that's a hyperplane. Here, half space is some line below, and then the line is the line, the boundary of the half space. So if you take n of these, you always get a unique point. In this case, take any 2 constraints, and you get the intersection point. Again, this also works in higher dimensions. And this intersection point is what we call a vertex. It could be outside of the feasibility region. It could be here, or it could be one of the vertices of the feasibility region, if you think of it as a polygon. Let me use the same name. But really, it's just the intersection of these hyperplanes. I guess that's a bit wrong. These are the hyperplanes, not the half spaces. They don't necessarily have just a single point at the intersection. Just from the picture, from the physical intuition, if you have some point in the interior of this yellow region, you can always move it freely in all directions. So in particular, you can move it in the direction of the improvement, the green arrow. So you can always improve it further. So it's never going to be an optimal point. On the flip side, that means you can always find an optimal point that is a vertex. The only other option would be that you have a whole edge that is optimal. Any point on that edge is optimal because you have a wall that's horizontal in that picture. But then still the endpoints of that wall would also be optimal. So in general, you can say there's always an optimal vertex. Could be many, or it could be several. So the optimal objective value is given by the value of some vertex. So that's this xi star. And that gives you some, now we finally reduced this annoying continuous problem that I'm always a bit iffy about, not sure how to solve it, into something discrete, because there's only so many intersection points, namely as many ways as I have to, as I can select n hyperplanes from all the constraints. So these are all the vertices, and in principle I could just go through all of them. And if n is small, that's actually polytime to brute force all the vertices. It's not how you want to solve this, because in general n can be big. I said millions in the beginning, so certainly you don't want to do m to the 1 million. But if n is really small, like in our examples, it's one option. And that's what the simplex algorithm does in a more clever way. It doesn't brute force all the vertices, but rather it starts at an arbitrary one and then always finds a neighbor that is better. And that means it follows some path along the contour and will stop as soon as there's no better neighbor. And then we found an optimal vertex. And what does a neighbor here mean? It means that it's defined by by an intersection of hyperplanes where only one hyperplane is different. You throw out one and you add another in. Okay, that's the geometric view. And you can write this as an algorithm. We're given the half spaces, and then you can conveniently say if their intersection is empty, the problem is infeasible. Otherwise, you find some feasible vertex. How to do that is another round of simplex. Let's ignore that for now. So suppose you're starting here with your x, and then you look if x can be improved, or if the green direction is hitting a wall, is going against some constraint. If that's not the case, then you can locally improve it. And so if that's a funny bit, if all the neighbors that are feasible are actually strictly worse, but you still can't locally improve, then the problem is unbounded. That case is a bit more tricky to see. That needed another picture, but let's ignore that case for the intuition. The typical case is there is some way to move in the direction of the green line to a neighboring vertex, and then you go there and repeat. Okay. Now this is a nice way to visualize things, and oftentimes you get the right intuitive ideas. For example, we can't necessarily say how many points we visit if we follow such a contour. And indeed, this is in general a problem of simplex. You can find contrived examples where there is exponentially many vertices, and you can also make simplex go to visit exponentially many vertices on its way to find the optimal solution. So oftentimes the geometry gives you the right way to think about the problem. If you wanted to implement it, it's not suitable. For that, you want to bring back linear algebra. And so I want to briefly introduce that other side of things, which is probably closer to what you've seen if you've seen it. The way I'm going to present it is take the other normal form, now with equality constraints. That's a bit easier to work with because now really you can work with these equalities, and all that is left of the other constraints is a non-negativity constraint. That means we have now many more variables than constraints necessarily to make the problem interesting. If that's not true, the problem is essentially either infeasible or has a single point, or that's easy to solve in all cases. So you should think now that there's many more variables than constraints. And now we talk about the matrix A from linear algebra point of view. And for example, for starters, we'll assume that it has full rank. So remember, because M is now smaller, the matrix A is wider than tall, because this is M and this is N. And so rank M means essentially that whenever you, or if it's non-degenerate and has full rank, whenever you pick a collection of columns, M columns out of the N possible ones, you get a set of linearly independent vectors. That's in general not true, but if you assume that the problem is such that you don't have redundant constraints, or things are not, there's constraints that are either multiples of each other, or they intersect several in a weird place. If you kind of ignore all these corner cases, then you can pick any collection of columns, and you get a basis for the matrix, which means just M independent, linearly independent vectors. Now you can split up your variables. So again, remember, J is a collection of columns, maybe these four. And then you can identify the corresponding variables that would be put on those columns as xj. These are the basis variables, those that interact with these columns. And you can separate those from the others, the non-base variables, just by their index, right? The basis variables have an index in this capital J and the others don't. Now, why is that useful? You can rewrite some of the things in splitting up the two parts to make progress. You can split up the constraints. So again, you take the matrix and now you take those four. That gives your matrix AJ. It's a square matrix now. And all the other columns together form this matrix AJ bar. And you similarly do that for the constraint, for the objective function coefficients. Then what we get is any feasible vector, so any x that satisfies the equality constraints, you can just rewrite, you split up that large sum into the columns that have index in capital J and the others. And so now this matrix AJ is square and has full rank, which means it's invertible. So you can find an inverse matrix and you can multiply the equation from the left with this inverse matrix. And then these cancel to identity and you can subtract this to the other side. So you get an expression for xj, the basis variables, as a function of the other variables. Okay? And that's, of course, is kind of clear if you have a certain number of constraints but more variables. You can fix some of the variables, namely exactly m minus n many. That's really n minus m here, right? N minus m many. And the other variables are then fully determined from the values you picked for the n minus m variables. Okay. Well, why is that useful? Well, in particular, you can set all the other variables to 0, and then you get a relatively simple vector x that solves the equality constraints, that satisfies the equality constraints. And these special kind of solutions, so the x's you get by taking some xj bar and setting it to 0 and computing the others from this formula here. That corresponds to the vertices in the geometric picture. Now, they may or may not be a feasible solution because in general, you don't know whether the base variables are satisfying the non-negativity constraints. They may be negative or not. But if they are non-negative, then they're a feasible basic solution. So to wrap up this slide, if you're given a selection of columns, any m columns out of the n variables, you can compute the basic solution and you can check whether it's feasible. Just check if it's larger than 0. Now the last bit is to make this step in simplex, check if we're optimal already, and if not, make an improving step. And that is easy from where we are now. So we have this basic solution where we think of setting xj bar to 0, so this whole term cancels. How can we locally modify this existing, suppose it's feasible, how can we locally modify our solution to improve the objective function? Well, what we cannot do is easy to see. We can't take any of the xj's and modify them because we would violate the equality constraint. And we can't decrease the non-base variables because that would violate the non-negativity. They're already at 0. So the only thing is we can increase the non-base variables and then maybe see what happens to xj, if that makes it feasible or not. So we can rewrite the cost function and that will tell us what to do. So that's the objective function. We can split it up the same way by the variable indices that occur in J and the others. Now we know xj, this is using for xj what we know about the basic solution. So you plug this in general. This is true not only for xj bar 0, but in general. Any solution that satisfies the equality constraints has this form. And now you can split up the two terms. So you have this part, which is constant, essentially. There's no x in there. And something in front of xj bar. And so this is the old cost vector. And then this new term here that combines, sorry, this shouldn't be here. That combines these parts. I guess the transpose is also wrong. Sorry. That should be just at the C. The matrix is already in the right shape. The key point here is this is some vector Cj bar. I guess that's why the transpose. So this is transpose now. You get a new set of coefficients for an objective function, and the overall objective function. Okay, I got to fix the. I'm staying here on the corrected slide. The overall objective function can be written as some constant plus some terms that depend only on the non-base variables. And these are the ones you're trying to modify. In particular, we try to slightly increase one of those and see what that does to the objective value. Well, if the coefficient that some variable here has is negative, then by increasing it, I'm only making, okay, we minimize, then I'm making the objective function better. Whereas if the coefficient is positive, I cannot help the objective value by increasing this xj. So you get no local improvement exactly if this thing is non-negative. Then any increase here would only make the cost higher, and that's not better. And indeed, that is, if you cannot locally improve, is the same as having a global optimum. That's because everything here is convex. We have a convex function over a convex domain. So whenever you have a local optimum, that's actually the global optimum. This is not true in general optimization, but because of the linearity, we get this simple criterion. You're only looking for a local optimum. And so that's essentially the end of this simplex algorithm. That's what it does. It computes these CJs. It checks if they're all greater or equal 0, then the current solution is the optimum and you can stop. Otherwise, there must be some entry that's negative. And then you know which of these non-base variables now becomes a base variable, and you have to kick out one of the base variables to move to a neighboring vertex. And that means, so you increase this variable, and you do that until some of the base variables drops to 0. And you can compute how far that is, so you can essentially use more linear algebra to do that step in a smart way. But that's really getting into the implementation. So let me wrap up at this point. So what we've seen is the conceptual ideas behind the simplex algorithm. It's a relatively simple and mostly combinatorial and discrete algorithm. It uses linear algebra to do the computations, but it's basically talking about these discrete objects as vertices on a polyhedron. Polyhedron is the higher dimensional version of a polygon. It's fairly easy to implement once you dig through the details, what the computations have to do. Implementing the implementations themselves is actually not hard. And it's usually the choice of open source solvers, just because of that. And it's also doing reasonably well anyways. Now, what I've said before, the worst case is actually an exponential. So simplex is not a polytime algorithm in the worst case. The details depend on how you do this last step. If you found some non-basis variable you want to increase and kick out another, there's usually some choice, and you have to pick a rule how to make that choice. And that depends how long it takes, but there's no such rule known that guarantees polynomial time. On the other hand, it is known that if you take any input and you slightly modify the numbers in it, you actually get an expected polytime algorithm with simplex. That's called smoothed analysis. I'm just mentioning this here because it kind of fits the theme of the lecture. But we're not going to dig into any of this in more detail. And last thing is, there are alternative methods that are more complicated, both to understand and to implement. But they are achieving this worst case polynomial time guarantee. Commercial solvers like Gurobi and so on, they often implement those, and these tend to perform best in large instances. For the lecture, all you need to take from this is a rough idea what simplex does, and the fact that you can solve LPs in polynomial time in theory and in practice. All right. Time for lunch. See you tomorrow.